So I come from the Department of Physics. And here we're going to talk about, well, so when I was a child, my parents told me that Santa has an invisibility cloak, right? That's why I never saw him giving the presents. And of course, well, I believe him, right? When we are children, we all believe these things. And probably they giggle, he's brilliant. But now I teach physics. And not only that, I'm teaching advanced optics. So who's giggling now? I'm not so gullible anymore. So I know it's impossible, right? Being invisible goes against all laws of physics. Or does it? So actually, there has been remarkable recent work on how we could achieve this. And I'm going to tell you. And some very simple demonstrations that are only very primitive versions of what hopefully one day could become something like Harry Potter's invisibility cloak. So first of all, what's invisibility? So invisibility is that you don't see something, right? So then I would change the question. What is seeing? What do I mean by seeing? And it's not so easy to say. So if I put my hand here, you all see it, right? So you can say you see it because it's in your line of sight. But that wouldn't really be correct, because if I turn off all the lights and it's nighttime, my hand is still in your line of sight, but you do not see it, right? So seeing means that light from somewhere is bouncing on my hand and then going into your eyes, right? And this is not easy. It was only found in the year around 1000 in the Book of Optics when they explain this. So light comes from somewhere. Light travels in straight lines, it reflects, and part of those reflections goes into your eyes, right? And that's how you see. Now, what does the brain do here? So the brain is seeing these rays of light coming from my hand, and the brain always assumes that light travels in straight lines. And so instead of having this picture of an eye here, let me put a more scientifically accurate cross-section of a human skull. So here we see the eye and the nerve that connects it to the brain. So now our eye is receiving these light rays, and it's just imagining that these light rays come in a straight line, so the brain imagines the hand is here. Why am I focusing on this, which seems kind of stupid? Because sometimes you can trick the brain. For example, if you have a hand and a mirror here, turns out that light doesn't always go in straight lines. It can reflect, right? However, the brain, our brain, will think that light always comes in straight lines, so we will see the hand at the other side, right? This is very easy. So I'm going through the basics, because later you will see we can do some tricks. Now, what else can happen? So not only can light reflect, but also, if you have a fish in a pond, light can refract, right? It changes the angle. And then the brain would see this fish as being closer to the surface. And this is actually something you can see if you look in a pond. Fish look always closer to the surface. Or if you have a pencil inside a cup of water, you can see that it bends. And this is because your brain assumes that light comes in a straight line, but actually it doesn't. So why does this bending happen? It's because of the refractive index of the material, right? So here we have a refractive index of air, which is 1. This tells us how much light is slowed down when it propagates in a medium. And here water is 1.33. And this change in the speed of light causes this refraction. Now, this is important. So this refractive index is the only material property that light cares about. So what do I mean by this? So when you have a material, you can ask many things about it. Is it a solid? Is it a liquid? How hot is it? Can you squish it? Many things. But from the point of view of light, we only care about the refractive index. I put an asterisk because actually the refractive index comes from 2 parts, an electric and a magnetic part, but we don't have to know this for now. So it only cares about the refractive index. And this means that if 2 things have the same refractive index, from the point of view of a ray of light, they are the same object. So this suggests a way of achieving invisibility. If you can have the same refractive index as your environment, you would be invisible. And this is what the famous novel, The Invisible Man, said. So you can inject something that makes your refractive index equal to that of air. And we have a demonstration here for you. Can we switch to the other computer? Okay, so what we're going to do now is we have these two beakers. This one has water, a refractive index of 1.33 or something like that. And this one has vegetable oil, the one we use for my kitchen, okay? So I'm going to show them here. So the vegetable oil and the water. And now I have this rod here, okay? And this rod is made of Pyrex with a refractive index 1.47. So if you put it in the water, of course you can see the rod. But if we put it into the oil, it turns out that they have the same refractive index, okay? So what happens is that from the point of view of light, oh, well, the rod seems to disappear, except from some tiny reflections because the refractive index is not exact. But you can see, right? So that's a way of achieving invisibility, having the same refractive index. It's actually more impressive here, right? So it does seem to disappear. So that's one way. But of course, it's a bit unrealistic because you cannot really turn. So can we switch back now to my other? Thank you. So that's one way of achieving it. But you cannot really change your refractive index into that of air because the refractive index depends on many physical properties of the atoms that you are made up of. So there is a second way, which is using refraction to redirect light. So let me show you how this would work. So let's imagine we have rays of light coming in straight lines, and we are observing here on the right. And we put a set of lenses, which we have right here, and I will show you now, which curve light, so light that is coming and hitting on the first lens is compressed, and then it travels in a narrower path, and then it expands again. So from the point of view of someone observing here, the light ray just came in a straight line. But you can hide things in this little place. So if we switch back to the other camera, so we have this setup of lenses, which you can see here. And you can see through it, right? So it's a normal setup of lenses. But here there is a region which is kind of an invisibility cloak. So let's see how it works. Can you see that? So you can see the background, but that makes it invisible. And that's because the light rays are compressed in this region, so I can touch around them. So actually, if I block the light rays at the very center, closing my fingers, eventually I block the light there. But I have a big region where this is invisible, so you can at the same time. So yeah, that's invisibility, a very simple setup. But of course this, so can we now switch back? Last time. So of course this only works when we are looking from where the webcam is. That's why we had this setup. Could we do it from, and this is actually a picture that you see the rays of light doing exactly what I showed. Could we do it from, have an invisibility cloak that works from many angles? So this is a proposal in which you just use this shape with different glasses that, due to refraction, make the rays of light seem as if they continued straight. And this works for 6 possible angles. And it's designed to work in a water environment. And actually, I have here a video. So you have this cloak here, and the part inside is invisible. And actually, now you will see at any moment, oh, a fish was inside the cloak there, right? Looking. And now I think the scientist disturbs the poor fish. Yeah, move. Get away from my cloak. And the fish says, okay. and goes away. Okay, so it works. But again, this only works for 6 possible angles. So it's kind of not convincing enough for Santa to sneak into our homes, right? So let's go to the serious stuff now. Now you understand what we need to do. We need to make rays look like they go through the object, even though they don't. So first of all, we need no reflection. So we remove that reflection of an object. Also, we need to see whatever is behind it. So we need rays to go around the object and continue as if they were in a straight line, so that our brain sees whatever is behind and thinks it's just a ray going in a straight line. And also, we don't want shadows, so any other source of light has also got to go around the object and continue forward. In other words, we need to have this invisibility cloak such that any ray of light from any direction goes around it, right? But here is a problem. So light goes in straight lines. Okay, we can have refraction, we can have reflection, but can we do curves like this? This seems maybe not possible. But actually it is. And you have all probably seen this optical effect in a hot day in a road, where you can see like a reflection in the road, right? This is because the refractive index of the air, since the road is very hot, is hitting the air. So it creates a gradient of temperature, and therefore the refractive index depends slightly on the temperature. So you get a refractive index that is changing smoothly from a certain value to another. And then the rays of light that enter this region are curved. And that's why your brain thinks this comes from a straight line, so you see like a reflection. So we can curve rays of light. The question is, can we curve them like this? So this is the question that scientists wanted to answer. Is it possible, even theoretically, and maybe do an experiment for this? So the question is, can we curve light at will? And I changed this question to another version. Do you know enough maths to do this? So right now I know you are GCSE and A-level students. So the answer would be, you don't yet have enough maths. You need to know to do functions with several variables. You need to know a lot of algebra, calculus, derivatives, lots of vectors, inverses, determinants. Many of these words you know, but you have to be very comfortable with this. And now I'm going to show slides that I showed to my physics students, but I don't expect you to understand them, so they will go very fast. But just don't be worried. So the question is, can we curve light at will? And maths helps us. We do this, we cancel that out, of course, trivial, easy, yes. So, maths answers yes. If you want the details, because you are very good at maths, you can go and read this paper, Controlling Electromagnetic Fields, in the journal Science. One of the best journals, or the best journal in all of science. So the answer is yes. So to summarize all those maths, this is what these maths are doing. You have a mathematical transformation of space, which I will explain in a second, and the maths are like a recipe that tell you what's the required refractive index that you need to put in a material to get the curves, to get the rays of light curving in the way you want them. So let me show you examples. So here I have drawn a rectangle. So this is space, right? So we have x and y. And this blue line would be a ray of light. And I can change its position and its rotation. And now I'm going to do a mathematical transformation of space. So for this, so the intuitive way to think about it is, imagine this space is like rubber and I can move it. So I'm going to do a mathematical transformation that twists this, like this. Okay, I twist this region. So I twist it. This can be explained, this can be mathematically described. It's just a function that maps a point to another point. And then this maths that I showed you very quickly will tell us what refractive index to put at each place in this region so that the rays of light follow this curvature. So this is what the actual ray of light would do in this material, following the recipe that math gives us. And the good thing is that this works for any angle and for any ray at any position. Okay? So that's very interesting. So now we can twist and do whatever we want with light. So in particular, we can do the cloak of invisibility. This is how it would work. So now we are going to do a different transformation. Instead of twisting space, we are going to open a hole. So we are going to get a point in the center, and we are going to expand it. So that I can do with this slider here. And I expand this hole. Okay? So this is a mathematical transformation, and our mathematical recipe will tell us what refractive index I need to place between these two rings, and that will be my invisibility cloak, such that all the rays of light go around the object. And this works for any angle and for any position. Right? So this is a recipe for a perfect invisibility cloak that would work for any angle, for any position. So this is the way that Santa could hide in this invisibility cloak. So here I'm picturing different rays of light all going around the cloak. And remember, this works for any angle. So if you are an observer here, all the rays that you're seeing, you see whatever is behind Santa. The bad thing of this cloak for poor Santa is that it's dark inside, because no light is actually getting into the cloak. But it's fine. It's a fine price to pay to being invisible, right? I think it's fine. So why am I not showing you this cloak here in the table? It would be amazing. So it's much more challenging. So if you follow the maths, it turns out that the material that you need to put in that cloak is anisotropic, which means that the speed of light needs to be different in different directions. So that's tricky to achieve with a natural material. We can do artificial materials, and people are working on this. Also, it needs to have a magnet. So I said that refractive index has two components, electric and magnetic. Normal materials have only the electric component, but this cloak needs to have a magnetic component, so it's also more challenging. So that's why nobody has ever yet done an invisibility cloak for light. However, they have done it for electromagnetic waves of other frequencies, such as microwave waves. This is the same as light, just with a different wavelength. And this is a two-dimensional invisibility cloak, so that if Santa was standing there, you would not be able to detect him with a radar, for example. So a radar sends waves, and this would be transparent to these waves. So this is really an invisibility cloak in microwave frequencies. Now the only question is bringing that frequency up to visible light, and then maybe we could do an invisibility cloak with visible light. So I hope I convinced you it's theoretically possible, not yet done in practice, but maybe in some years it can be. So thank you very much for your attention.